Okay, so this recording is to help with the Unit 8 lab and discussion. So we're going to start by getting some equipment. So coming up, let's see, the lab is 8.04. So for those of you that are on track with things, that's coming up later this week as far as being due, or you can search for it under the class plan if you're getting to it late. You just got to remember that it was 8.04. And then, let's see, I think light pink is this class. Yeah, so 8.04 right here. Click more. So the lesson introduction and laboratory gives you some kind of background information. I highly suggest reading that, especially if you're not already familiar with what Half-Life is. Then a couple other things that you'll want, and I believe this is going to be in the lesson introduction, is the lab report, just because it helps, not that you're turning it in, because this is a discussion-based assignment, but it's useful to kind of help you organize your thoughts, okay? And these are the questions that your assignment is based on. So, let's see. I'm going to get that downloaded and open. That's a Word document. For the actual lab itself, you're going to want your laboratory manual, your laboratory guide, that book with the neural on the cover, and you're going to focus on calculating half-life lab, which should be around page 55 where it starts. Okay, I'm using my online version so that it's easier to share with you guys. But again, you can read through here. It takes you through what a half-life is, some questions to kind of get you going and thinking, and then it takes you to your materials and your lab procedure. So one of the things is that for materials, it tells you to get 100 of the same coin. If you don't have 100 of the same coin, you can do other things to get through this. For example, I just cut out a bunch of little tiny pieces of paper, put an X on one side, and there's no X on the other side. That way I have a head versus tails. Okay. A couple of other things that I made that are going to help me kind of get through this is for the actual lab experiment, I set this up. So what you're going to do is you're going to go through 10 trials. You're going to shake up the box, dump it all out, and then you're going to, I think it's you remove you keep the heads and you remove the tails. Okay, so for me, I'm just going to call the X's the heads. I'm going to keep those, and I'm going to get rid of the ones without X's. So I have this set up to kind of keep track of my numbers. At the end, you're going to want to graph that data. And this is actually going to be an extra credit opportunity for you if you post this graph. You'll have to take a picture of it, and you'll have to upload that to your discussion assignment. But if you post your graph, I will give you some extra credit points. And then that was kind of extra on top of what the lab instructions were telling you to make. But then this table, and we'll go through and talk about this table at the end after we've gone through a couple trials with the pennies. Okay. All right. So it's going to be a little while till we get back to that question sheet. What we're doing right now is, let me show you where it is in the procedure here. All right, so create a data table with the following columns: trial number, number of heads. The table should have enough rows to include 8 trials plus 0, okay? The number of heads for trial 0 will be 100. Title the table results of coin flip. So I need to add my title there. Results of coin flip. All right. And you'll repeat this part of the experiment 3 times to leave columns for 3 number of head results. All right. So I'm just going to show you one set of this, and then it's up to you to do the rest. And then it shows you this table to do later. We're not going to talk about this table until we're done with our trials. Okay. But making the half-life with a coin flip. You're going to shake your box and empty the coins under the table. Separate them from in the heads and tails. So for me, it's going to be X's and no X's. Count the number of heads. Each head represents one atom out of the sample of 100 that is not decayed. All right? So let's do this. So what I did, this box, so if you don't have a box handy, this is actually what your mortar and pestle was in. So I'm just going to shut this. And the big thing is you want to shake it really well, up, down, side to side. Okay, and then I'm using paper out of one of my corners. Right, and then you just dump it on the table. A couple that got stuck. A piece of tape in here that they're getting stuck on. All right. Now I'm going to go through and separate them out. So that, try to flatten things so that you're not flipping them as you separate them. But I'm separating my X's and my non-X's. Okay, so those all have X's on them. That has an X. Those all have X's. Oops, I accidentally flipped that one. So if you accidentally flip something, you probably won't run into that issue if you're using coins. Coins are heavier, which is going to make particularly separating and not accidentally flipping a little bit easier. They also are less likely to stick to each other. Going to the wrong pile there. But if you don't have coins, this is a good option to go with to make sure that you're able to do this. All right, so ideally, probability-wise, about how many of each should we end up having at the end? What do you think? So long as everything was able to kind of get separated and we were going with a true 50-50 ratio here, we have 50% chance of getting an X on top, a 50% chance of getting a non-X. So it kind of depends on how things work out. But these non-X's, they decayed. They're gone. All right. Ideally, we're hoping we have about 50 left, but probability is not certainty. So we may have a different number than 50. So I'm just going to start lining these up by 5s because that's going to make it easier for me to count. And I think just based on the size of this pile, I'm going to end up with more than 50, but we'll see what happens. So obviously, not all of my pieces were cut to the exact same size. All right, so I end up with 1, 2, 3, 4, 5, 6, 7, actually 36 left. Okay, so apparently I lost more than half of my sample there, which is fine. So I'm going to, actually, yeah, 36 left. There's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, yeah. 1, 2, 3, 4, 5, 6, 7 times 5 is 35 plus 1 is 36. So on my handy dandy table over here, I'm going to write 36. Okay. Then I'll put it back in the box and do it again. I know why there's so few left. I didn't get all of my pieces out of the box. There's some back there. So let's finish dumping those. This may not be the best box to do paper with. It could seem odd how many of that were left. And there's one more stuck in there. There's a few more. Alright, now, so I had 36. Let's separate these out. And I'll have to add this to my 36 number. Oh, I'm going wrong way. All right, so those are not x's, those are decayed. And I need to add how many to 36? So I have 1, 2, 3, 15, 18 plus 36 is 54, right? Yeah. Okay. So just easy, I adjusted my table. I ended up with 54 at the end. So now what I'm going to do is I'm going to put these back in the box. And like we did before, I'm going to do it so that they are facing up. I'll do my best not to flip these when I put them in. Now I know the next time I need to check those little side flaps, make sure there's nothing stuck. And I put these in when I finish again. So there's my 54. All right, and shut it. Shake really well. And dump those back out. I have some stuck again. All right, I think I have them all out this time. I don't see any left in the flaps. So let's split these up based on whether or not they have an X or no X. X, X, no X. Those all have X's. Those do not. X, X, no X, no X, X. So notice it goes a little bit faster once you kind of have a feeling of what you're doing. Plus, as the numbers get smaller, it's going to go faster. Okay, so the first couple are going to be a little lengthy just because of the number of pieces you have. But eventually, when you get down to only having 20 left or something like that, it'll go a lot faster. All right, so those are decayed. And I am left with 2, 3, 4, 5, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 3. So 1, 2, 3, 4, 23 left. Okay. None of these are stuck to each other. So 23. And I'm going to put those back in my box and continue this. Okay. So you kind of get the idea here, I think, with you guys. I don't want you to have to, you can, if you kind of get the idea, you can fast forward to get to what we do with these numbers when we're done. I might cut it a little bit short, but right, that's stuck. These all have X's. So decayed. And then I am left with 1, 2, 3, 4, 5, 6, 7. I have 10 left. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 11 actually. All right, so I'm going to add 11 on here. And it's more, keep going until you have 2. Once you hit 2, things are going to start. Or if you get to the point where you only have 1 left, then obviously you're going to stop. But so if you don't make it to all 8 trials, that is okay. Eventually, you're going to get to such a small number that you can't split it in half anymore. So there goes 5, and I'm left with 6 left. All right. So some trials might go more, or some of your experiment might go farther than this. You won't always get the same numbers. All right, what am I left with? All right, I've got 2 left. So I made it 5 trials. I'm gonna call the quits there because at this point I'll either get perfectly ahead in an X and a non-X, or I might lose both of them, or I might get 2 X's. So at this point you're kind of running down into too small numbers to really continue. So what I'm going to do is I'm going to take my data and I'm going to plot it. So at 0, I had 100. At trial 1, I had 54 left. At trial 2, I had 23 left. At trial 3, I had 11 left. At trial 4, I had 6 left. And at trial 5, I had 2 left. So the graph is turning out correctly. You should get this inverse curve or opposite of exponential curve. Okay? It shouldn't give you a perfectly straight line. Really what's happening with a half-life is you lose half of the atoms, or about half of the atoms, every time a half-life passes. Okay? So you can do this 2 more times. And then let's talk about this chart. Okay, so carbon-14 is something that is used to date things like fossils and things like that to an extent, right? So what we're dealing with is, so kind of how I interpreted this table and how to fill it out is time passed. So if 0 half-lives have passed, then that means no time has passed. So you have your total amount at the beginning, right? Once 1 half-life has passed, that means there's been 5,750 years. This is the known half-life for carbon-14. So you start with your million carbon-14s, and at the end of that period of time, you have half of that many left, or 500,000. Okay? So this is where having, if you're not real strong with your math, having a calculator handy would be nice. So what I'm going to do is 2 half-lives is going to be 2 times 5,750, or 11,500 years. You're starting out with the number of carbon-14 you ended with before, and now that's going to be divided in half, right? And then another 5,750 years is going to pass, so we're at 17,250 years, right? So we're starting with that 250,000 carbon-14, and we're ending with 125, right? And then for 4 half-lives, I'm going to add another 5,750 to get 23,000 years have passed, starting with 125,000, because that's what we ended with before. Then I divide that by 2, and I get 62,500 carbon-14 left. Okay, so something that is 23,000 years old would have, if they started with a million carbon-14 at the very beginning, they'd have only 62,500 left. Okay, so if you're taking a sample and you're trying to date it, and you discover that based on parts per million, it has 62,500 left, then you know how old it is, right? 4 half-lives have passed, then you're at 23,000 years. So 23,000 plus 5,750 brings you up to 28,750 years. You're starting with the 62,500. And you're going to divide that by 2, leaving you with 31,250 carbon-14. Okay? So I'm hoping at this point the pattern is kind of starting to make sense. What you do, this column, you just keep adding 5,750 because that's the length of 1 half-life. This column is what you wrote in the row above, all right? What you ended with from the time, the half-life before. And then you just take this column and divide by 2 to get the very right column. All right. So that brings us to the lab questions. So this first question, number 1, definitely is going to play into that table that we were talking about here. So this table. Okay. So use table 1. And then this one's talking about things in a little bit different of a deal, but if you wanted to find the fractions, all right, what you could do is if you take this last column, so you take 250,000, and you divide it by what you started with, all right, which is a million. 250 divided by a million is 0.25 or 1/4. Right? So if you kind of keep doing that until you find the decimal that's the same as 1/16, that's one way you could do this. All right? You can also think of it as every time you go through a half-life, the first time you divide by 2, so that's 1/2. When you divide again, it makes it 1/4. When you divide a third time, it makes it 1/8, and so forth. Okay? So for question 2, this one, a couple things you're going to have to do. One, you're going to want to look up a couple of things. First, look up when Homo sapien, that's humans, all right? Figure out when they first showed up on Earth's timeline. And then figure out when dinosaurs first showed up on Earth's timeline. Definitely going to be a huge difference in numbers, all right? So if you think about it, again, looking at this table is going to help, especially when you get down here and you find out how many atoms you have left when you get through 10 half-lives and how many years it's been. And that's going to help you decide why carbon-14 is good for something that hasn't been around as long as the dinosaurs. Okay? Because when you get to this bottom area down here, you're going to be talking 57,000 years ago. $57,500 years ago. So that number is going to be more realistic for human leg bones, all right? Especially when you figure out how long ago it was that the dinosaurs were around. But you need to put that into your own words using the numbers on your chart here to explain that answer, okay? All right, last one. Potassium-40 is a radioactive material that decays into argon-40. The half-life of a sample of 40K, or the potassium-40, is 1.3 billion years. Rocks containing potassium-40 have been around since the formation of the Earth, and argon-40 gas has been accumulating in those rocks since the Earth formed. However, when rocks are heated by volcanic action, all of the argon-40 leaves the rock when the gases escape. Create a scenario and discuss, based on your knowledge of half-life, the value of potassium-argon dating to geologists. Okay? So this is the question where if you really get the idea behind half-life and what it can tell you, and which of those substances, either the potassium-40 or the argon-40, which one is actually more meaningful, that's when you're going to get this question correct. Okay? And, if you're having a hard time with this question, try looking it up. Right? These are things that scientists use on a regular basis. So there's going to be stuff out there that explains how they use it. So if you're not quite there just from doing the lab, look up potassium-40 online and the uses of it and why they use it, things like that. All right, so last thing, just to make sure we're all clear on this. So this lab report isn't actually getting turned in, but what you are doing is, let's see, 8.04 has only these assignments in there. So if you go down to 8.05, discuss calculating half-life, this is the actual lab graded assignment, and it's a discussion assignment. And So up here. If you notice, your discussion questions are the same as the lab report. All right? So the more detailed your discussion is, the more likely you will get full points. Make sure you answer all parts of the questions. All right? And if you get stuck on number 3, because that one's definitely going to be a trickier one, you might want to try looking up how scientists use potassium-40 so you get a little bit more background on it. All right? But one big thing is how long it lasts.